Welcome, everybody. You have found your way into the first Lowbrow meeting of 2026. I'm Charlie Nielsen, the president of the club, and I have been forever. It seems like someday it'll change. But anyway, we're a gang of about 120, somewhere around there. Maybe we'll get a number of amateur astronomers. And
213.
213 is it now? Okay, 213.
The report came out.
So, yeah.
Thanks.
As tradition would have it, we always have our guest speaker the first part of our meeting. So if somebody wanted to come and just see that part and didn't want to stick around for our highly engaging and entertaining business meeting afterwards, we might let you escape. So we would understand. So speaking of which, our distinguished guest tonight is Dr. Fred Adams, who's actually spoken to us a number of times, and we've enjoyed it each time. He's a professor in the U of M physics department, but he specializes in astrophysics, particularly star formation, cosmology, and the early universe.
And he bowed to the inevitable. Now he's pivoted to the Secretary of State race, and that is a wide open situation.
Yeah, Secretary of State would be one of the most interesting, convention seats to watch. There's so many people eyeing this. A lot of people who, to that point, have been in the race longer than Gilchrist now.
I can't hear anything on the web.
Same here. It's
Nope.
still nothing.
Yeah.
Here we go.
Is that better? What changed?
Much.
All right. Yeah.
Just make sure you turn it on and talk, and it should be.
Right. Okay, thanks. Okay, well, we certainly have our glitches tonight, huh? So anyway. Fred could leave everybody if he really wanted to gasping for oxygen, but he has a particular talent for taking very complex ideas and putting them in a way that people can understand it. You don't have to be an astrophysicist to get what Fred's talking about. He is now also the director of the Lineweaver Institute for Theoretical Physics, which is actually an entity that lives here in the physics department. But being director is not that big of a deal because part of his whole job is just letting people know that it even exists. Tonight, Fred is here to talk to us about the formation of Jupiter and other giant planets. So I'm very pleased and honored to present our friend and honorary University Lowbrow member, by the way, Dr. Fred Adams.
Well, thank you, Charlie. I'm very proud to be an honorary member of this esteemed institution. So it's also a pleasure to be back to talk to you guys. Today, I'm going to tell you about the general picture of how planets form. In the spirit of full disclosure, this is a derivative of a talk I gave a couple of years ago, which David, I think, was the only person in it. So,
Yeah, I was there.
yeah, so, if you have any questions, you can ask David afterwards. He'll know everything. He'll So, no pressure.
Oh, no.
So, what I want to talk to you about today is a lot of things. So, this is sort of an outline of what we're going to go over. I want to sort of begin by giving you an overview of the landscape of exoplanets. We've now discovered 6,000 of the things, which is kind of amazing. So some of you are old enough, I believe, to remember the year 1995. Some of you are not. But those of you who are, there were no planets discovered, right? And now we got 6,000 of them. And it's kind of amazing. And I'll tell you, so we want to know how they all formed, okay? Now, it turns out that these planets form in the circumstellar disks that are formed alongside stars when the stars themselves formed. And these disks provide the initial conditions for this planet formation process. Because of that, I'm going to spend a little bit of time telling you about disks and disk properties, and only a little bit. Now, it turns out there's two different ways to make planets. You can make them from the ground up, and you can make them from the top down. So I'll tell you a little bit about both
Dr. Adams, I hate to interrupt, but your projection's not on full screen mode. It's showing the computer screen.
Oh, well, it's showing full screen here.
Yeah. Here, a different screen.
So
Just
we'll stop share. Share. Share again. So.
Entire screen.
It's not necessarily true. Oh, at least I'm waiting forever.
Okay, but now I have to alter stuff.
Is it still, how's it there? Same thing. So. It's powerful, but it's asking a question. Continue on that screen. Continue to share, stop sharing PowerPoint.
See, I don't have that on my screen.
I know, it's because it's on the projector screen. It's an alternate.
I could read it okay on this smaller size.
That's weird. Can't clear that message right there. Might alt, Jeff, alt tab. See if you can get to it. On your screen. Does it show it on yours? Does it show that on your screen? Nope.
Interesting.
Oh,
It's gotta be the U of M computer then.
yeah. Is it coming off of
computer?
Is it coming off the Apple or is it coming off the U of M computer?
It does not appear on the laptop.
Yeah.
It's on mine, so.
This is the.
Doesn't say yes.
Yeah, there you go. Hit enter.
I don't know if that'll work. I don't think it's connected to the same. Here we go.
Oh.
Well, I don't know. Yeah. Did it continue?
All right.
Are they saying it?
Well, they're seeing it, but they're not seeing it in the full screen mode. They're seeing it in the presenter mode.
Yeah.
So, well, I can stop sharing. Now.
It's identified as monitor 2. Can you share screen too? There you go.
Yeah. Is that the secret place?
Yes.
Okay.
Need to hit an enter though. There's still a message up there.
That's it.
Means being recorded. Okay. Yeah, but it blocks. Oh, that moves this. No. So you got to get to that screen somehow, but it's on the Mac, not on the.
It's not on my Mac though.
But it's driven from your Mac. It's from that screen 2 on your Mac.
Oh.
So you're looking at screen 1. So if you mouse over, you might be able to get your mouse onto that.
There you go. Yeah, you just passed by.
There you see. There you go.
No.
Yep, you're there.
You can go look at that house.
Right.
Yes.
Oops, a little too far.
Of course, it's gonna disappear when he gets right there.
So where's this person? I can't see it.
Mouse down just a bit.
It's off to the side already. Oh, never mind.
Okay.
Yeah, there you go. So I would ask what could go wrong next, but I'm afraid to find out.
Executive correctly.
Not by this division.
Executive motion.
Okay, so perhaps we should continue. As I was saying, there were two ways to make planets. You can make them from the bottom up, you can make them from the top down, and I'll tell you just a little bit about those two processes. It turns out that the bottom up process produces most of the planets. And that's how we think our planets, including our Jupiter, formed. So we're going to spend most of our time talking about that. Now, one of the things that I'm going to emphasize to you is that something called a super Earth is an important part of the process. So since this is a mystery story, I'm going to give away the ending right now. Okay. So what is a super Earth? Well, it turns out that in our solar system, we have terrestrial planets like Earth and Venus, which have one Earth mass of the planet, or one Earth mass of mass, right? Earth is conveniently one Earth mass. Yeah. And just by coincidence.
Yeah.
And then we have Jupiter and Saturn, which Jupiter has 316 Earth masses, Saturn has 90, and then the ice giants, Neptune and Uranus, have about 20, a little less. But the point is that most solar systems, as we'll see, have most planets being about 10 Earth masses of rock. So a 10 Earth mass rock is called a super Earth because it's big and people are very unimaginative, so it's super Earth, right? And it turns out that in the planet inventory that I'll show you, that's the most common kind of planet. So many people have said, well, our solar system is unusual because it doesn't have any super Earths. But it actually does. It has 4 of them. They just happen to be covered by gas and living inside Jupiter, Saturn, Uranus, and Neptune. And in fact, most of the rock in the whole galaxy is in the form of super Earths, including in our solar system. I will come back to that point. But if you don't remember anything else from this talk, when someone says to you, our solar system is weird because it doesn't have any super Earths, they're wrong. Okay. So you'll see, I'll make that point. Now, if I have time at the end, I'll tell you a little bit about what these things look like when they're forming, and I'll tell you a little bit about a recent work that Charlie wanted me to talk about why we think our Jupiter started with a radius twice as big as it is now. Now, the fact that it started bigger than it is now is not actually a surprise. What's cool about that result is that you can actually play CSI solar system and go back 4.5 billion years ago and see anything at all about the planet when it was forming, and actually do that with some kind of fidelity, right? So that's where we're going, and we're 20 minutes into the talk already, and we only have 3 hours to go. So let's see. Here we go. So this is the obligatory plot that everybody has to show if they ever talk about exoplanets. And what you see here is we're plotting the planet mass as a function of the planet's semi-major axis, or essentially orbital radius. We won't worry too much about eccentricity today. So what you see is that there's a wide range of masses and a wide range of semi-major axes. Our solar system planets are here. Here's Earth and Venus, and then Saturn and Jupiter are up there. And what you see is that this part of the parameter space down here, where planets are small and far away, are hard to see. And the planets that are big and close to the star are easier to see. So the limit of what we can see is basically this line here. So these planets here, or this region of the parameter space here, corresponds to planets that are very difficult to see, and that's why there's nothing there. But you see that for the part where we can see the planets, they're kind of filling the space everywhere. We have planets at all radii and all masses. And the masses are measured in Jupiter masses. So they go all the way up to almost stars at the top and things as small as Mercury and Mars on the bottom. And those guys are so small, they're not even really planets, right? So we have this full range. I'll say what I mean by that more. Now you can also look at the eccentricities if you want. So here I'm plotting the same planets with similar major axis, but instead of plotting the mass, I'm plotting the eccentricity. That's how elongated the orbit is. And what you see is that most of them are sort of moderately eccentric, and there's a few that are very eccentric, and there's no planets in the upper left. That's actually not unexpected, because if you're in the upper left, you're very eccentric. And if you're very eccentric, you come very close, the planet would come very close to a star, and then it gets tidally disturbed, and it basically gets sucked into the star. It takes billions of years, but these things are billions of years old, so we don't expect planets to be in the upper left of this diagram, and we don't see them, okay? So this all sort of makes sense. Now, the one thing you want to talk about when you talk about planets, or actually any astronomical object, is what is the distribution of masses? So if you're talking about stars, you want to know how many big stars, how many little stars you have. If you're talking about galaxies, you want to know how many big galaxies, how many small galaxies you have. For planets, we want to do the same thing. Now, even though we have 6,000 planets, that's actually not quite enough because as soon as you start dividing it into different categories, the number in your bin gets pretty small. Long story short is that we have a crude estimate for the mass function for giant planets. Even though we have 6,000 planets discovered to date, most of them are not giant planets, most of them are smaller. And of the giant planets, we only have so many. So here we have a mass function with 4 bins, and you see that it looks pretty flat. What I'm plotting is just a histogram of the number of planets in each bin. The bins are logarithmically spaced. That's important. What that means, since nobody wants to do math this late at night on a Friday, what that means is that a flat line here corresponds to a function that's 1 over m. Which means there's more little ones than big ones, but only, well, by a factor of m, right? So there's 10 times more Jupiters than 10 Jupiter mass things. There's and there's 10 times more sub-Saturns than there are Jupiters, right? And you see that this mass function is flat. This was done in 2021. Oh, I was going to show you another plot that shows the same thing. Now, where this sort of shows where this comes in is that I've now zoomed out. So I'm plotting all the masses all the way to the very largest star, which is 100 times the mass of the sun, all the way down to the smallest rocks. And the part of the parameter space that I'm showing you here in the previous slide is here. And it increases like 1 over m because of what I said before, okay? So, next up. Another curious part of this parameter space, or this data set, is that when we look at all the multi-planet systems we discovered, okay? See, when you look at planetary systems, you don't want to just know what planet property is for one thing, you want to know what the whole system property is, right? We live in a solar system. We have 8 planets, or so. I don't know how you guys feel about Pluto. You can discuss that among yourselves. But when we look at multi-planet systems, we see something very curious. These are plots of about 40 multi-planet systems. They have names that are not particularly informative. But what you see is that the spacing of the dots on this plot correspond to the spacing of the orbits. The size of the dots correspond to the size of the mass of the planets. And if you look at that plot very carefully, you see 2 things that are very striking. To 0th order, as in broad brush terms, the spacing is pretty regular. We have planet, 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 planet. There's not like a big gap, or there's very rarely a big gap. They're pretty regular. And within the same system, they're all the same size. You can see that, right? That's kind of uninspected. And it's not that all the planets are the same size. these guys are smaller than these guys, but all the ones of this system are the same size, and all the ones of this system are the same size. So astronomers always give silly names to things. So we call this the Pisa to pod phenomena, that all these planets, which are very much the same, they have equal masses and equal spacing. So we call that the Pisa and the pod systems. So here is a, well, I won't bug you with the math at this point. I'm only going to say that you could do the statistics on this and show that the statement I'm making is not just something you see by eye, but rather it's something that's statistically significant. It's very statistically significant. You would not just get this by random chance. In other words, there's a real trend. When you make a solar system, the planets like to have equal spacing, boom, 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 and they like to have equal mass. It's not that you have this distribution of planets and you just draw them randomly, put the solar system together, but you have this very well-ordered system. And the typical semi-major axis ratios you get from that sample, in other words, if you take all the planets I showed you and just take radius of one orbit divided by the one right inside it, you get this nice hump. They're all kind of between these two green lines at about 1.5.
Nice.
Yeah, they're all nested by an even factor. And that's kind of unexpected. You can look at that in a different way. And what you find is that there's a nice, well-defined hump there, and they're not actually close to resonance. For those of you who know about resonance, you get special effects when the period ratios are exact integers, like 2 to 1 or 3 to 1 or 3 to 2. And those are these guys here. And there's very few planets. There's a little bit of extra 3 to 2s, but otherwise it's pretty smooth distribution. So there's not a preference for resonance, which is kind of surprising to the astronomers. It may or may not be surprising to you guys, but it is actually surprising to the astronomers. The other thing about the sample that I want to talk about is going back to giant planets. What we want to know is we want to know what the occurrence rate of the giant planets are as a function of orbital period. In other words, do big planets form close to their stars or far from the stars? Where do they form? Where do they want to form? Now, again, for those of you who are old enough, in 1995 we discovered the first extrasolar planet. And if you remember, you probably don't, it was in a 4-day orbit, which is crazy because our Jupiter is in a 13-year orbit. It orbits with a radius, semi-major axis, is 5.2 times that of the Earth. Okay, so in that sense, Jupiter lives 5 times farther from the sun than Earth does. But the very first planet that we found was what we call hot Jupiter, and had a 4-day orbit, which means it's really, 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 really close to its sun. Okay, and then this is 1995. Over the next 10 years, a good majority, or sizable fraction anyway, of the planets we found were also these hot Jupiters. So everybody said, well, that means that our understanding of planet formation is wrong. That planets like to form next to their sun, and our Jupiter is an anomaly. Now, the story that I'm going to tell you, and this really will take 3 hours of this reading, the story I'm going to tell you says that the sweet spot for making a planet, from a theoretical point of view, is actually right where our Jupiter is. And I'll tell you why. Okay. The reason why is that if you're interior to Jupiter, it's hotter. And the little tiny rocks that make the planet want to be coated with ices. But guess what? It's too hot. Ice melts. It turns out that most of the mass that's not gas is in the form of ice, not rock. So the little tiny rocky things, the building blocks of planets inside what's called the ice line, have 3 times less mass than outside the ice line. Also, if you go outside and you try to make a snowball, icy things stick together. if you go to the beach in summer and you take a sand and sand balls don't stick together. They hurt more when you throw them at your brother, but they don't actually stick together. So if you imagine, and basically the little dust grains that are in the solar system are basically sand and graphite, right? They're silicates, right? So the sand ball is an apt analogy. So the point is that it's really hard to make a planet inside the ice line, and it's much easier outside the ice line. But if you go too far out, the orbits get slower and slower and slower and slower and slower, so it gets harder and harder to make a planet. So the sweet spot to make a planet is right where Jupiter is, because that's right outside the ice line. Okay? Then all the planets we found in the first decade, not all of them, but a good fraction of them were at 4 days, which is not at 5 AU. Now this plot here shows what we think we have now. If you look at the rate of finding planets as a function of period, and you fix or you account for all the selection effects, the fact that it's easier to see big planets close in and it's harder to find farther away, you see that it peaks at a few thousand days, which is just inside Jupiter. Now you can do this a bunch of different ways. Here's 2 more compilations of it, because you have to account for the what's called the selection effect, the fact that it's easier to see planets closer to their stars. When you do that, you can do it in a bunch of different ways, and I won't go through all the detail, but you see all of these things peak right where Jupiter is. So what we find is that the sweet spot to make a planet is right where Jupiter is. That's what we were saying in the 80s, but we didn't have any data. And then the 90s came and we had data and it said, well, we were wrong. And now that we have enough data, it turns out we're right again, okay? And this is just the slide for what I just said. Planets like to form just outside the ice line, because if you go just outside the ice line, which is at 3, 4, 5 AU, depending on how bright your star is, if you're outside there, the rocks are coated with ice, it's easier to make things, and you have more mass. So that sets up the question. This is the review of what our planet sample looks like. And what we're finding is that the lessons here are twofold. 1, there's a lot of super Earths. 2, there's a lot of regularity in multi-planet systems. And 3, Jupiters like to form where our Jupiter is. And what we would like is we'd like a comprehensive theory that will let us understand how these systems come to be and explain all of those properties. Now, of course, that's a tall order. It's going to be hard to do in the next half hour, but we'll get as far as we can get, right? And we're still working on it. We don't have a complete predictive 100% bona fide theory of this yet, but we made a lot of progress, and that's kind of what I'm going to report to you. So we need a mechanism to produce all these planets. Now, the story starts with the star formation process itself. Stars are being formed in our galaxy today. They're formed in these molecular clouds of gas. The molecular clouds have masses of 1 million or so times the mass of the sun, and little subunits inside of them collapse. And we have this picture of star formation where the subunits collapse and they're rotating. So when they rotate, they form not stars, but solar systems. That's important because the parcels of gas that ultimately collapse to form stars, because they're rotating, not all of the stuff can get all the way to the center. In order to carry that angular momentum, some of the stuff has to remain at larger radii. Now here's the cool thing. If you take the properties of a molecular cloud, like you see in the sky, and this was an actual picture of one I showed you on the previous plot here, there's an actual cloud. If you take the properties of this cloud, and you see how fast the little subunits are rotating, you can calculate how far they can collapse and still retain their angular momentum. But they don't collapse from this big interstellar size down to the size of the sun. They collapse down to about 30 AU. Maybe 40 AU. In other words, the natural size that they collapse to is the size of the damn solar system. And it fits really, really well. Then, instead of forming a single star, with all the mass there, you form a star with a extended disk around it. Then the disk will dump some of its mass onto the star, And then some of that mass will be coagulated into planets. And that's what we want to talk about. So here's another picture of that process. So the typical radii that you expect are about 10 to 100 AU. There's actually 5 different ways in which we predicted this, okay? A little bit of a humble brag here. This is what I wrote my thesis on in the 80s, okay? So if you just take the rotation rates of the little parcels of gas and let them collapse, they collapse down to sizes of 100 AU, okay? But you can also look at the radiation coming out of forming stars. And in order to understand what you see, what you find is that there's a deficit of hot material. And that means some of it's getting hung up at larger radii. And that larger radii gives you a radius, which is 100 AU. Then when you look at star disk systems, you can look at their spectral energy distributions and see how far out they go. And then there's cutoff. And I think I have a picture of that. Because we can now see that. And you see that as you go to longer and longer wavelengths, you get a cutoff. And the size of this cutoff is determined by the size of the disk. And the size of the disk you read off is 100 AU for this particular thing. And then this was predicted in 1987. And then this map, finally, a few years ago, we could actually take a picture of them. And it's 100 AU in size. So we knew it was going to be, but now we have pictures of many, many of these things, and they're all 100 AU in size. So we have a good handle for the properties. And the two most important things you need to know about are that the sizes of the disks are basically solar system size. And the masses of the disks have a maximum of about a tenth of the mass of the star. Okay. If you take our solar system planets, which are mostly rocky, even Jupiter is more rocky than the sun, right? And you take our solar system planets and you put the gas back in, you could ask how much mass would there be? And the answer is about 3% or 4% or 5% of the sun, depending on how you do that calculation. What this data is showing, don't worry about the details, is showing that the maximum disk mass that we see is 10% of the stellar mass. So the picture that emerges is that when you make a star disk system, it's thermostated to have only 10% of the mass of the disk relative to the star. And the size is 180. And those two numbers are the most important things you got for the beginning of this planet formation process. So when you ask, how do planets form and where do they form and what's their environment? The environment is a disk that's roughly solar system size, and it can have no more mass than about 10% of its sun. And our solar system is very much commensurate with that. It doesn't have quite that much mass, but that's okay. So that's the upper limit, not the lower limit. The other thing we know is that we see these disk signatures in different clusters, different star forming regions with different ages. So we can see how many disks we have as a function of age. So this is the fraction of systems that have disks as a function of age of the region. And you see that at 1 million years, everybody has a disk. And at 10 million years, only 10% of the systems have disks. So you can actually fit an exponential to that and find a half-life, which means that after 3 million years, half the disks are gone. After another 3 million years, the other half of the half is gone. After another 3 million years, only an eighth are left, and so on. And it kind of works pretty well. And what this tells you is that the disks don't last forever. They last for millions of years. Most of them will last for at least 3 million years. Very few of them will last longer than 10 million years. Now remember, our solar system is 4.5 billion years old now. It takes only a tenth of a million years to make the sun. And then it takes another 3 to 10 million years for the disk to go away. And that means for the planet formation process, it has to play out in 3 to 10 million years, because after that, there's no more raw material. It's like the trucks come and take all the lumber away. You can't make a house after 3 million years because there's no raw materials anymore. I'm going to skip this in the interest of time and just go to the end. So the star formation process naturally produces these disk systems. We can now actually just take pictures of them in the sky, which is amazing. And we know their properties. Their properties are they're about solar system size, 10 to 100 AU. They have masses that are up to 10% the mass of the star. They have power law surface density distributions, which is kind of what you always get in astronomy. And they have lifetimes with a half-life of order 3 million years. And from this process, or from this starting point, we have to make planets. And to skip this too. Now, as I said in the intro, there's 2 ways to make planets. You can make them from the bottom up, and you can make them from the top down. To give away the story, both mechanisms operate, or so we think. But most planets formed from the bottom up, not from the top down. And let me tell you why. Well, if you want to form from the top down, then gravity is the force that organizes things. And the way gravity works is that it works better if you have bigger things. Because there's more gravity. Pulls more mass, means more gravity. You can pull things together. So if you want to form a disk from the top down, you need a very heavy disk. And it turns out when you do the calculation, we argued that disks start with only 10% of the mass of their star. So that's the most mass you can have. And when you start with 10% of the mass of the star, and you are sufficiently unstable that you can make a secondary body, this is a very crude numerical simulation from 1992 of this process. What you get is only a fraction of the material collects into a secondary body. The natural size scale or mass scale of the object you form is about 10 Jupiters. Now, 10 Jupiters is sort of in the never, never land. The smallest star is 80 Jupiters, and Jupiter, coincidentally, is 1 Jupiter. Okay. So the largest planet we got in our solar system is 1 Jupiter. The smallest star is 80 Jupiters. This mechanism produces things that are 10 Jupiters. So they're not really planets. They're kind of too big to be planets. And they're not really stars because they're too small stars. They're sort of slacker stars called brown dwarfs. They just sit around on their mom's couch, play video games all day. Because they don't get around to doing anything. They don't burn hydrogen. They don't do anything useful. They just hang around. Now, this was done in 1992. And we argued at the time that gravitational instability produces brown dwarfs, things that are 10, 15, 20 Jupiters. Then if you dial yourself forward, people have done these simulations for the next 30 years. Xiaoan Zhu is a very good numericist who's a grad student here at Michigan, is now a professor, and he's got simulations that show the same kind of spiral arms and little condensations, and he gets brown dwarfs at 180. There's another, I didn't show the other slide. There's an even more recent study that was published last year that gets brown dwarfs at 180. And then we can actually see these things in the sky. Here's a collection of brown dwarfs with large semi-major axes. In fact, there's 3 of them in this system. And they're basically brown dwarfs at not quite, but almost 180. So this process does happen, but it doesn't happen that often. And when it happens, it makes brown dwarfs at 100 AU. It makes 10, 20, 30 Jupiter mass objects, things that are too small to be stars, things that are kind of sort of too big to be planets. So we think, that's just a summary of what I just said. You don't form planets, you form brown dwarfs at 100 AU. And the objects that we see that correspond to those are probably those in the box up there. They're the large things that are far away. I should also say that when this gravitational instability in the disk sets in, it sets in most naturally in the outer part of the disk. And since the outer part of the disk is at 100 AU, you get objects that are far from their stars. Now, it is possible for planets to move around a bit, so they don't always stay there, but that's where they tend to be, and that's where they fall. Okay? So that leads us to the main event. How do most planets? How did our giant planets? They form from the bottom up, or moving. And the process by which they form from the bottom up, we have to give a name, so we call it the core accretion paradigm. And it basically happens in 3 stages. The first stage is that rocks accumulate into bigger rocks and accumulate into bigger rocks. There's 2 ways for that to happen, which I'll talk about. But as long as the rock is small, it doesn't have that much gravity, so it doesn't really hold on to much gas. If you think about Earth, the planet we live on, it does have some gas, the atmosphere we're breathing. But, and it's very important, but it's also very small. Almost all the mass is in the rock, right? There's no mass in the atmosphere. And there's a reason for that. Gravity's weak. Gas is hard to hold on to. So in order for a planet or a rock to be big enough and bad enough to hold on to an atmosphere, it kind of has to be about 10 times the mass of Earth. So what happens is that rocks accumulate and get bigger and bigger and bigger, and then nothing interesting happens until the rock is bigger than or as big as a super Earth. Now, once it's 10 Earths, then it has enough gravity to start holding onto its gas. But then there's another problem. So we enter into the second phase of the process, ingeniously called phase 2. And during phase 2, this big rock, which is now 10-ish Earth masses, holds on to gas. But there's more rock than gas. So the gas is very puffy. That's the technical term for it. And what that means in terms of thermodynamics is that it takes a long time for it to cool. So it has to cool down in order to get cold and compressed. And that just takes a long time. Now, once the atmosphere itself is heavy, which means it has a mass bigger than the rock it's around, then its own gravity will crush it. Then you're in business, because then the new gas comes in and compresses itself, and then more gas can come in. And you enter into the third phase, where this accretion process runs away. So this is the process by which most planets, we think, form. So to recap, you have stage 1, where you build up rocks. You have stage 2, where you build up the initial atmosphere, but it takes a long time. And you have stage 3, where you're making a planet, where most of the gas comes in. So most of the gas comes in stage 3, but most of the time is eaten up in phase 2. So it's this race. Remember, the disks only live for 3, 4, 5, 6, 7 million years. It takes about 1 million years to make the rock. Then it takes millions of years for this phase 2 to happen, when the rock gets slowly, or the rock and the gas surrounding gets slowly bigger. And then once you're at a certain threshold and you degas rapidly, that happens in less than 1 million years afterwards. So guess what? Since the disks only live for 3 to 10 million years, and it takes 3 to 10 million years to get to the stage 3, sometimes you'll win the race, sometimes you lose the race. So sometimes you make your giant planet, and sometimes the disk goes away before you can make the giant planet, and what are you left with? Well, the rock that was trying to make the planet that failed. That looks a lot like the super Earths I showed you dozens of a few slides ago. So there's more failed instances of giant planet formation than there are successful instances of giant planet formation. That's what we expect, given the time scales involved, and that's what we see in the data that I've showed you today. Now, I want to go through this in just a little bit more detail. So let's go back to the first stage. We have all these rocks that are orbiting around in the solar system. I already said that if the rocks are coated with ices, you have more mass in them and they stick together, so you can build things more rapidly. That's why it's preferable to make things in the outer solar system. There's many processes that happen, but let me just tell you about a couple of things. Here's the thing. If you have these little tiny dust grains, they're kind of start to be really small, only a micron in size, but they will coalesce pretty rapidly until they get to be about this size, which is supposed to be gravel. Okay, you know, gravel you could hold in your hand, centimeter size little chunks of rock. The dust grains will readily coagulate into gravel. Okay, no problem. Where the problem comes in is what happens next. Because once the rock is bigger than about a meter, so not a centimeter, but a meter, then given how fast these things are bashing into each other, when you bash 2 meter-sized things together, instead of sticking together and making a larger thing, they break apart. That's a problem if you're trying to make a planet, because you just go back to gravel, right? You have these meter-sized things, and they break apart into gravel, and you have a problem. Okay. Now, the way around that is there's what's called a streaming incident. Now, I'm not going to explain this in great detail because it would take 3 hours and you still wouldn't be very happy with my explanation. So let me tell you 2 things. What happens is that if you can imagine you're in the situation where the density of the rock and the density of the gas that it's living in are the same, then you can have new effects happen. I should ballpark or preface this by saying, in the ordinary situation, in the disk before we do any processing, and this is true of the sun too, there's like 2% of the mass in rock and 98% in gas. And 90 is bigger than 2, right? So most of the mass is in gas. And if most of the mass is in gas, then gravitational instability happens on the gas, and you need big things, and we make 10 Jupiter mass things, as we've already discussed. But if you can have the rock and the mass of the rock and the mass of the gas comparable, then they can act together. The gas is enough presence to actually slow down the rocks and make them coagulate, but it doesn't get in the way. And again, the process to describe this is mathematically very complicated. But once you reach that sweet spot, you have instability set in. And the instability will coagulate these gravel-sized rocks into planetesimal-sized rocks. You'll jump the meter barrier. And once you're as big as a planetesimal, which means a good fraction of a kilometer, hundreds of meters, then gravity is strong enough that even if you crush things on collision, they still hold together gravitationally, and then you're still good. They'll recoalesce. So if this is true, then we can jump the meter barrier and get planetesimals. Now, here's where a cool U of M result comes in. You guys are the University of Michigan Lowbrow astronomers after all, so Michigan connections are not disallowed, right? So here's the deal. In our solar system today, Neptune lives at 30 AU, which you guys probably know more than all of us, right? You look at Neptune, right? It's very cool. Beyond Neptune, though, there's a bunch of little rocks. Well, kind of big rocks. They're called trans-Neptunian objects or Kuiper belt objects. And they live from Neptune as far out as, well, out to about 46 AU or so. But here's the thing. There's this guy, Kevin. We have this grad student who, there's a whole team of us that are looking at solar system objects. But Kevin was the grad student who did this analysis. And he did this cool analysis where you take pictures of the outer solar system, and these things are faint, so they're hard to see. You guys know more about this than I do, of course. But what you can do is you can take a bunch of pictures every hour, every day, and then you can stack them together. But these objects are moving. So you have to know which way it's moving in order to stack it the right way. But you don't know which way it's moving. So what you do is you do all the possibilities. you stack it every way it can go in any trajectory it can go and see what you see. Now, if you find a bona fide object, then the trajectory you get will be actually obeying Kepler's laws, which we actually know. So you can verify that it works. And once you found it, you can then track it and rediscover it, right? So this guy, Kevin, found 2,500 new objects in the outer solar system. Let me show them to you. He made a little mosaic of all the pictures of them. This is actually a genuine object that he found. They weren't actually in this particular pattern until he put them there. But nonetheless, that's what he found.
A useful mosaic.
It's very good. But there's more to the story, and this is actually probably the coolest part of the talk, although it's very subtle. So, if you take all of these new objects, there's only 2,300 of them, 2,500, I misspoke earlier. You can make a distribution of them. So you're plotting how many rocks you have at each magnitude. So these are fainter and smaller on the right side, and they're bigger and brighter on the left side. You can think you know the albedo and turn it into a size if you want, but the observational result is in magnitudes. As again, you guys know more about it than I do. Okay, so we have this magnitude distribution. Now, if you look at this carefully, it looks kind of like a power law, but the data are actually different than a power law. There's a curvature to this, which is real, and I can magnify it for you. If I put this on its side and show you the data points, you see that they go up above the line and back down. What that means is that there's a preferred size of these 2,300 new objects. It's not a super well-defined period, but it is a bona fide size. And it's the size of the planetesimals you predict that would be produced by the streaming instability. This is the first and only evidence that the streaming instability actually works. And if the streaming instability works, then we have a way to get from the meter-sized things to planetesimal-sized things. And we have all these leftover planetesimal-sized things in our outer solar system for Kevin to see. At least we got 2,300 of them. There's actually more in the survey that haven't been published yet, which will be dumped on you later. But anyway, there's thousands of new objects that we're finding. And the if you go back to the previous slide, the previous data actually only go out to about here because they couldn't go faint because they didn't have this computational capability. Except for one data point that's way out here. It's not on the spot, but it agrees with the very faintest one. That was done by Gary Bernstein while he was a professor here in astronomy. So he has since moved to Penn. So this is all fitting together. We're starting to see the residual rocks, which were the building blocks of the planet. They're consistent with the story of the streaming instability. And that means that we have a way to get to rocks that are 100 kilometers or more. Okay. And then once you have those rocks, they can collide. And in the inner parts of the solar system, and by inner, I mean where Jupiter is, there's a lot of them, and they're dense, and they can collide, and you can get big things like the core of Jupiter. Now, here's the thing. When you mash particles together, there's two ways to do it. You could have big things hitting big things, and then the big things hit even bigger things. Or you can have one of these big things eating the gravel, because there's a lot of gravel left over. We call the gravel pebbles because we have to give things multiple names to confuse you guys. Now, here's the thing. If you have a rock that's growing and it's eating smaller rocks, it can grow and grow and grow until it gets to about 10 Earth masses. Once it gets to be about 10 Earth masses, then it's actually hard to grow any faster or any farther. And the reason is a little bit subtle, but I'll try to explain it. The little rocks are subject to gas pressure, and there's gas around. So they obey what's called the Bernoulli equation. And when you squeeze gas together, it goes faster. So if you put the rocks in orbit around something big, they go really fast. And if they get squeezed together and go really fast, then they fly out and don't get accreted anymore. So you can't make a rock too big, otherwise the Bernoulli principle will keep you from eating more rocks. And the speed limit, or the mass limit, is about 10 Earths. It's about the super Earth. So that means that the super Earth scale, the 10 Earth mass scale, is super important, okay? It's super important because, as I argued, a good fraction of the actual planets we see are super Earths. They're not giant planets. You need to get to super Earth size, 10 Earth masses, in order for a rock to eat gas and become a giant planet. And if you look at the inventory of rock in our solar system, you take all the stuff that's not gas. Well, Jupiter has about 20 Earth masses of stuff that's not gas, rock and ice. So does Saturn, so does Uranus, so does Neptune. Venus and Earth have one Earth mass of rock. This is Mars. See, Mars isn't even really a planet, right? When it comes to its content of rock, right? We should throw it out of the solar system just like we did Pluto. I know there's probably some Mars fans there, they're going to be mad at me. And I'm just saying this to wake you up, right? But the point is that most of the rock in our solar system are in the cores of these giant planets. And this plot here just shows the area proportional to the mass, so you can see this very visually. All the rock in our solar system is in super Earths. All the rock in the whole galaxy is in super Earths. So super Earths are the thing. But that doesn't get us to a giant planet. We have to go into phase 2. So in phase 2, the rock eats gas, but the gas gets spread out. It has to cool in order to be compressed, and it takes a long time for it to cool. Now there's an outer boundary. Next to the rock, the gravity of the rock wins. But if you go far enough from the rock, the gravity of the sun or the star wins. The boundary between them is called the Hill sphere, after some little guy named Hill that did this like in the 1800s. And this boundary here in this plot sort of depicts the Hill sphere. So what happens is that during phase 2, this super Earth's starting to eat gas, but it can only do so slowly because it can't cool. But once enough gas gets packed in there, the gravity of that gas crushes it, and then you can eat gas fast. And then the planet enters into this phase 3. And during phase 3, you get something very much like the star formation process, okay? Because you get a central object, which is now the planet, but the material that's coming into the Hill sphere is in orbit around the sun or the star. So it's got angular momentum. And because it has angular momentum, that material doesn't fall all the way to the planetary surface, it collects into a circumplanetary disk, just like the material we saw during the star formation process accumulated into a circumstellar disk. So you get sort of a mini solar system forming with a planet in the middle, a disk around it, and then stuff raining onto it. And this is what happens during phase 3. So what you need to keep in mind is that most of the mass is gathered in this phase, and most of the material actually doesn't fall directly onto the planet. It falls onto the disk and then works its way onto the planet. So I'm officially out of time, but I'm going to keep going for just a little bit longer. But what I can show you, because I'm going to not give you quite all the detail I might otherwise, what I can show you is that by piecing together what the structure of these forming planets look like, I can calculate for you the radiation coming out of them so you can see what they look like, okay? So the basic picture is that, let's see, where am I? Here. You have material falling from the Hill sphere onto the planet, onto the disk, The disk is acting, it has viscosity in it, which is like friction. So that means the material will spiral from the disk onto the planet and dissipate energy. So the net effect is that all the stuff falls from a large distance and ends up on the planetary surface. And along the way, it dissipates its energy, and that gives you this energy source. Now, some of the energy sources, some of the energy is dissipated right on the surface of the planet, and some of it's dissipated off the disk on the way in. We can calculate all that. The good news is that we have calculated all that. You don't have to. I won't even show you the equations, but you can do it. And that tells you, it's like putting a light bulb in the middle of this thing. You can figure out where all the photons are generated. And then you can do the radiative transfer calculation to see how they work their way out of the system. So let me skip ahead. We can calculate the density of the stuff falling in. It's going to have a non-spherical density distribution, but if you spherically average it, you get simple power laws. That's important. And don't worry about the formulae. It's important because what it means is that not all of the material can fall all the way in. And that means there's less material close to the planet than there would be if the system wasn't rotating. And that means more of the photons can get out without being processed. So the object will be bluer in color than it would otherwise. We can also calculate the surface density of the disk and see where material is, or the energy is dissipated. The inner boundary is set by magnetic fields. The planet will have a strong magnetic field, which we'll come back to in a minute. And it doesn't affect how it looks that much. But what it does is it affects the inner edge of the disk. Okay, so this is the forming planet. There's a disk that's like 4 times the radius of the planet further out. And the material from the disk can't get any further in because the magnetic field is pushing it away. So the material that's coming in through the disk can't accrete onto the planet directly, or the planet directly. It has to climb up the field line and move on. Now we can calculate all of this. And we add all the luminosity together. And we do the radiative transfer to see where all the photons come from. And then I'll show you what things look like. Okay, so the parameter space for a forming planet, so I'm going to show you, has 4 variables. You can have different masses. You can have different mass accretion rates. You can have different locations for the planet. Like this one's at 5 AU, which is where Jupiter is. Jupiter's really at 5.2 AU, but this one's at 5. And then you can also have different magnetic fields. The magnetic field sets the size of that inner cavity. So it sets the inner boundary condition of the disk. Now, in this particular set of spectral energy distributions, I'm keeping the mass accretion rate constant and the location constant in the magnetic field, or the inner boundary constant, and I'm varying the mass. So as you make the planet go from small mass to big mass, it gets more luminous. But it also, frequency increases this way, and wavelength increases this way. So it gets bluer. It gets brighter and blue. Now you can also fix the other things and increase the mass accretion rate. That's the rate at which stuff is entering this Hill sphere. And here it gets brighter as the mass accretion rate increases, but it gets red. You can change the inner boundary condition and you just change the shape a little bit. And you can also change the location. So as you make the location of the planet go farther and farther in, the spectral energy distributions get narrower and narrower. The narrower range of temperatures emitting, and you have a narrower spectrum, or spectral energy distribution. Now here's the thing. You might ask, well, why am I going on about how these things look? The program that we'd really like to do is we'd like to build a theory of cloud formation, which I've outlined for you I don't know whether it's in more detail you want or less detail that you want, but I've outlined the theory of light. And then to test it, you want to see what the photons are when they come out. And this is the answer. Now, to test it, you not only need to calculate the photons or the spectral distribution, but you have to compare it to observations. Okay. We don't have enough observations to test it yet. We have 2 data points so far. So this is a disk around a star. And these little tiny blobs that you can barely see in this picture are allegedly one of these forming planets that I'm talking about. And we have a tentative detection of them at 1 wavelength. Okay. And since this is a couple years old, there's a couple more. And my point is, we're just now at the cusp of being able to look observationally at planets in the stage of formation. And in 10 years' time, 20 years' time, 2 years' time, I don't know how long it will take, we'll have enough data that we can measure full spectral energy distributions. In other words, do this experiment at different wavelengths and see what those curves look like, and compare them to the theoretical curves and mix and match and figure out what works and what doesn't. We're just at the start of that. What's that?
95 all over again. 1995 all over.
Yeah.
One planet.
Yeah.
One case.
Yeah.
Building from there.
But you got to start from that. This is where we are as of this moment, right? Now, I'm going to tell you one more thing before we close down. This is a long walk, okay? But Jupiter now, in its present state, has 1 Jupiter mass of material, and it has a size that's conveniently 1 Jupiter radius. You guys are not impressed by that. It's a nice coincidence, all right? Okay. Now, what you might want to know is, well, how big was Jupiter when it was made? Now, we expect that when you make a blob of gas like Jupiter, it will start bigger and it will contract. So we expect the number to be bigger than 1 Jupiter radius. But how much bigger? Twice as big, 3 times as big, 10 times as big, a billion times as big. How big should it be? The other thing that happens is that if you have a Jupiter that's a young Jupiter that's this big, when it shrinks down to a smaller size like it is now, it's not talking to anybody. So it has to conserve its angular momentum. But if you have something big and you make it smaller, it will spin faster. This is the ice skater effect that we're about to see in the Winter Olympics in about 8 months, right? If your ice skater has her arms out, then she brings them in, she spins faster. You get to see this, right? Well, Jupiter does the same. It starts with a big radius and it shrinks and it spins faster. So here's the story. When Jupiter was first made, it had a disk around it, like I was telling, okay? It had magnetic fields that are truncating the inner part of the disk, like I was telling. And it had moons inside of it. Now, I think all of you guys are very, very well of what are called the Galilean satellites. In fact, Galileo was the first amateur astronomer. He was the lowbrow before the lowbrows were here, right? Because he made the telescope, and the first thing he did is he found the Galilean satellites. Io is the innermost Galilean satellite, okay? And we think that the Galilean satellites formed not quite where they were now, but they moved around, okay? Now, it turns out that there are 2 little tiny moons that Galileo did not find. There's actually a whole bunch of little tiny moons around Jupiter that I could not keep track of. But there's 2 that I can tell you about today. There's Amalthea and Thebe, okay? They're 2 little rocks inside of Io. Now, why do we care? Well, these are the canaries in the coal mine that will ultimately tell us how big Jupiter is. And it's a cool story. You might not believe it, but it's still a cool story, okay? And here's the story. So Io and its friends moved around. When Io or any planet is in a mean motion resonance with a little planet like Thebe or a little object like Thebe, you get a lot of excitation. It's hard to do, but you can calculate how much excitation you get. Okay. So what happens is you have this disk, you make the Galilean satellites, you have the two little moons inside. Then the disk has to go away. When the disk goes away, then Jupiter's mass is set. We'll call that the moment of Jupiter formation when the disk goes away. Okay. At that time, Io has to be somewhere. You can quote me on that. Okay. Now, if Io is too close and it moves around, it will excite the inclination angle of the inner moons. If Io is further away, it will excite them less. Now, turns out we measure the inclination of the two moons to be very specific numbers, 0.36 and 1.09 in degrees. Now, these numbers aren't important other than these are what they do. If Io is too close, you would excite these numbers to be bigger than they are. If Io is too far away, you don't excite them enough and you can't explain why they have these values. But if Io is in a range of about 4 times the radius of Jupiter, then you're good. Okay? So we kind of know where Io was at this moment of formation. Then you can make another argument that's saying, well, if Io is inside the disk, it has to be just a little bit further in outer, or the inner part of the disk is a little bit further inside of Io. So if we know where Io is, we know where the inner part of the disk is. And the inner part of the disk, we think, is set by the magnetic fields. So if the planet has magnetic fields, as shown here, and it's tied to the inner part of the disk, then when this moment of formation happens, Jupiter will be rotating at the orbit corresponding to this radius. So we now know how fast Jupiter is rotating. Then if we apply the conservation of angular momentum, the ice skater argument, we can see how fast it should be rotating now. Or we could work it back the other way and say, well, we could just measure how fast it's rotating now. So we know how much angular momentum it had to have back then, which tells us how big it had. And that tells us how big Jupiter was at its moment of formation. And the answer is 2. It's twice as big as it is now. Which is not a crazy number. It's kind of sort of what you expect. So it's not a revolution in, oh, this is completely changes the game, but it's a way in which we can go back in time and see what properties of a planet were when they were formed, right? So this is just the rest of the argument. And here's the answer. You get the size of Jupiter then is twice the size of Jupiter now. So I'm going to close down. Let me just give you a few of the highlights. The things that I think you should, well, I'm hoping that you'll remember from this discussion are that we have a theory of planets, okay? We have 6,000 planets observed. They have a collection of properties that we talked about, and we have 2 theories for making them. The core accretion paradigm, I think, accounts for the vast majority of the planets that we see. Now, we talked about how a lot of the high metal, rocky, and icy material in the universe likes to live in the form of super-Earths, and super-Earths play a particularly important part of our story. Most of the rock ends up in them. Most of the planets we see are in the super-Earth category. Most of the giant planets we think form through the core accretion paradigm, so they have a super-Earth in their core. And you also need super-Earth-sized core to eat gas to become a giant planet. So for all those reasons, super-Earths are the thing. And then we also saw that planets tend to form near the ice line. And even though the planets move around, it doesn't change the picture that much. We haven't had time to talk about that. And finally, I would argue that our own solar system fits nicely into this paradigm. The fact that we have one big giant planet, which is Jupiter, and 2 failed giant planets, which are Uranus and Neptune is perfectly consistent with the time scales of this picture of core accretion that I talked about. The fact that Jupiter lives right beyond the ice line, which is the sweet spot for making big planets, is also consistent. And the fact that we have well-ordered rocky planets in the inside is also consistent. Although they're a little bit less ordered than some, they're pretty well ordered as well. So our solar system is not an anomaly. What is true, however, is that just like there's a lot of diversity in the human population, there's lots of different ways to make a people, there's lots of different ways to make a solar system. Our solar system is one of them. It's not particularly weird, but it's also not particularly common. It's just one of the many ways you can make a solar system, but it's perfectly consistent with the picture of how we think they're made. So this is probably a good place to stop. I'd be happy to stay as long as you want, take questions, and thank you for your attention.
In the case of low mass stars, is it possible for a planet to form at a faster rate than the star does, so that you could have a gas giant forming within what would later become the ice line?
Probably not, but never say never. It's hard for planets to form as most stars form in the same time scale, which is a 10th of a million years, and it's hard for giant planets to form in that smaller time scale. So we think the stars form in an order of magnitude faster time scale than the planets. So we have this kind of well-defined ordering. You make the star first, and it has a disk. And by the time the planets get around to making them, the disks have the properties that I tried to explain or tried to outline. And the observations are, at least, they don't prove it, but they're very much consistent with that. And I think you in the blue had the next question.
You talked about the 3 million year mark where planets in the race to accrete gas.
Yes.
But it seems that the total gas that's in the disk, eventually all of it's going to be accreted by something.
Well, you have this, yes and no. So let me explain. You have the star and you have the disk. The disks will start with 5% of the mass of the sun or star, 10%, 3%, some good fraction, but not too big. Where does it go? It goes to 3 places. Part of it gets incorporated into planets. Part of it gets hoovered onto the star. And part of it gets evaporated away. Photons from the star get heated and evaporated. These stars live in clusters, so the outer parts of the nebula get heated from the outside and get evaporated. So for all these reasons, the gas is going away for 3 reasons. It's getting locked into planets, it's getting accreted onto the star, it's getting blown away from the outside, and the inside photons also act to blow it away. So all the gas is going to these 3 places, and it's a race as to how much goes to each of the 3. So it's a competition. Thank you. So like you and the beard is next one, I think.
I'm trying to understand string instabilities. Basically, the pebbles are getting caught up in the viscosity of the gas, and that's effectively moderating the relative velocities, and that's allowing them to collide slowly enough.
Yeah, I'm not going to be able to give you a perfect explanation, but let me give you a try, okay? In some sense, gravitational collapse is a competition between gravity pulling stuff in and pressure pushing stuff out. So if you just imagine you have a collection of just gas, like the air in this room, I have gas inside this ball here. The pressure is the pressure. There's not much mass inside this volume, so there's not much gravity. So it's not pulling together very much. So this is not collapsing. But if I get big enough, keep the density the same, the temperature the same, the pressure the same, but I get big enough in mass, the mass grows. I can eventually get big enough that I collapse, right? So if I have enough gravity, I'll beat the pressure and I'll collapse. So if you imagine you have a disk, the same thing happens. On a large, if you just have gas, then you have to get to this 10 Jupiter mass size scale that we talked about to collapse. If you just had rock, then the rock itself can collapse to smaller things, if and only if it can get to really, really cold velocities. if it's coupled to the gas, if there's more gas than rock, then it just goes along with the gas and it never gets cold enough to do that. But there's this sweet spot where you have equal amounts of gas and rock. So the gas can slow down the rocks and they can get to high enough density where an instability like what I just described will happen. And that will make larger objects than pure rock collapse. It will make planetesimal collapse. And that's what the streaming instability is in a nutshell. And I understand that's not the super sort of comforting kind of explanation, but
Is it like Navier-Stokes theory for motion of all these things? We're looking turbulence.
yeah, it depends on all of those things. That's why it's complicated. If you put in more turbulence, you've got to get to bigger size scales, and you describe that with the Stokes number, as you said, and so on. So it's very complicated, but the general picture is you need the rocks to, you need a situation in which the rocks can get to a dense and cold state so they have a chance of going unstable. And
It's like supersonic expansion, the interior.
well, it's not supersonic, they need to be subsonic. So yeah. So let's go to the guy next door.
That ratio of the 10% of the accretion disk it's about a 10% of a star. Is that the same as like in a binary system? Multiple stars working off each other. Also, does that affect the freeze line? Like, does it push it further out?
Oh, well, no, it's a little different. So the story here is that if you have a star and a disk around it, if the disk has more mass than about 10% of the star, then it has enough mass to have enough gravity to make really strong spiral arms, like you see in galaxies. And if that happens, those spiral arms, they're called spiral instabilities, go nonlinear, and they dissipate energy and they dump material onto the star. So you can never get a lot heavier than 10% of the mass and the disk relative to the star. Otherwise, you find that instability set in. Now, here's the thing: the instability set in on the orbital time scale of the outer disk edge. So even for 100 AU disk, which is how big you grow them, that, Kepler's laws gives you a 1,000-year time scale. But we make the star over 10 to the 5 years, which is 100 times longer. So the spiral instabilities can always keep up. They'll always dump material. If the disk gets too big, it goes spiral instability and dumps stuff on the star, and then more stuff comes on and it gets rinse and repeat. So you end up with a disk that's somewhat less than, but as much as 10% of the star. So you just kind of have this sort of threshold. Yeah. Now, sort of binary is a very interesting question because sometimes we see equal mass binaries. So how the heck did that happen? And long story short is we do not have a definitive theory for binary information yet. I have a half of an answer. You might call it a half-assed answer. But nonetheless, the answer is that because of what I just said of how disks work, if you want to make a binary, you don't make a primary and then a disk and have a fragment. If you do that, you'll get a brown dwarf. If you want two big stars, instead of forming a star and a disk, you basically form a pancake. So the difference is that a star and a disk means the disk is actually in centrifugal support with Keplerian or nearly Keplerian orbits around the star. If you just collapse the thing to a big pancake, it's just a mess. From that mess, the lowest energy state will have two accumulation centers. And then you have two things that can fight for mass instead of one. You can have disks around each of those two things and around both of them. And then it's a fight, it's a competition to get enough mass. And that is how binaries.
Yes.
And then the difference between the two states, why do you get one or the other, is that two stars, especially two big stars, equal mass stars, have a lot of angular momentum. A single star and a disk, so the disk has to be small, we said, has less angular momentum. So we don't know the details, but the high angular momentum starting states will give you more binariness, and the low angular momentum starting states will give you more solar system binariness instance.
Just the combined mass of those, like if there's a disk after it's two stars, does that create the spiral every time? eventually, or sort of eventually like, will it eventually reach that 10% level even in a binary system? Like, will a disk eventually form, even if it's a pancake together, just because?
Oh, yeah, once you have well, eventually, yes. But the idea is you pancake first so that you get two centers instead of one, which will eventually be 2 stars instead of 1. Now, sometimes you could get a hierarchy in a third thing. And sometimes we do see triples. You guys see triples, right? And sometimes you see quadruples. But usually they're very hierarchical. If you have 3 things that are too close together, you'll throw one of them out from the net supports. You've been very patient. So
You're saying that Jupiter's semi-major axis is right where you'd expect it to be, where it wants to be.
just outside the ice line, yes.
Okay. It's always been there?
Well, yes and no. It's possible for the planets to have formed and moved around a little bit. So we don't know exactly where they formed and how far they moved, but there are many, many simulations. There's like 1,000 papers that have tried to make scenarios of just that. The ones that are the most believable make the 4 giant planets in a slightly more compact configuration than they are now. So instead of extending from 5 AU where Jupiter is to 30 AU where Neptune is, you smush it. So maybe Jupiter started 4 AU and Neptune started at 20. So that's very plausible. It actually makes Neptune form a lot better. And if you move Neptune out from 30 to, or from 20 to 30 AU, it gets pushed out by rocks scattering off at each other. It will snowplow these Kuiper objects that I talked about and hoover them up into some mean motion resonances, which we see sometimes. Not strong, but not all of them, but some. And that works nicely. If you push Neptune out several AU to where it is now, from some smaller radius to where it is now, you can hoover up these things into the mean motion resonance configuration.
So the grand tack theory is not negated.
It's not negated, but I think the short answer to your question is that the planets do in fact move around, but they probably move around into a very modest amount. It's very important for Neptune to form a little bit sooner. The rest of it don't matter. But and it's very hard to make a Jupiter a 5 AU and then move it all the way into 4 days where we see the hot Jupiters. So hot Jupiters have to be rare. So one of the things I didn't get a chance to say is that even though we found hot Jupiters to start with because they're easiest to see, the occurrence rate of giant planets altogether is something like 20%, as in 20% of the stars have a Jupiter of some kind. But only 0.5% have a hot Jupiter. So hot Jupiters are actually quite rare, which makes sense. It's hard to move something so big so far. But it can happen sometimes. But the most common thing is to have a Jupiter that doesn't move very far. And that's what we got, and that's the most common thing. Now, it could have formed at 4 AU and moved to 5. That's fine. It could have moved from 3 to 5, I don't know. But it's not moving huge distances. It's also true that it's a lot easier to move Neptune than Jupiter, because Jupiter is 15 times bigger in mass, right?
So show the picture of all the solar systems and how the planets were about the same size. The gaps between them were about the same size. Just so I can understand it, is our solar system in that, right? I mean, does our solar system match that?
That's a very good question. I don't know if I have the plot in this talk, but I have a plot somewhere, and I'll tell you what it shows. So the solar systems I showed you in that plot are what I would call inner solar systems. The periods go from 4 days to 300 days, okay? Earth is 365 days, right? So we can compare, well, actually some will go a little bit beyond 300 days, but it's like our terrestrial planets. So the question you can ask, if I look at our terrestrial planets, which have 4 planets, if you count Mercury and Mars, Jupiter, Venus and Earth are damn near the same, right? And the spacing is nuts, right? Venus is kind of half as far in as Earth, and Mars is kind of twice as far out. So it's kind of a factor 2. There's the tightest Bode law that people talk about the spacing in our solar system. So very well spaced. The masses are a little bit not as uniform because Mercury and Mars are a little bit more. So what I could do is I could take all of the 4 planet systems we've seen, including our terrestrial planets, and I could rank order them in how ordered they are. Okay, so the ones that are most ordered on top, the ones that are least ordered on bottom. Where does our solar system fall? 20% bottom, which means that 4 out of 5 are more ordered than our terrestrial planet systems, and 1 out of 5 are less. So we're in the distribution. We're a little bit less uniform in mass than many that I've showed. The standard is to be more uniform. But we're not crazy outlier. 20% or even worse, right? Yeah. It's like you're taking a class, 80% of the kids do better than you, and you do better than 20%. So we'll count that as a win, right? Any other questions? Thank you for all your patience.
I have a few questions. Go ahead.
Go ahead, Doug.
Oh yeah, I had a few questions about your graphs. Do you want them all at once or one at a time?
I'll just do one at a time.
Okay. First, on your magnetic radii graph, what were the blue and green lines?
Oh, well, I have 2 lines on that. One line showed field lines from the planet that truncate the inner edge of the disk.
Mm-hmm.
The other line, which is the upper line in that plot, shows that the fields are actually strong enough that when material falls from above, it actually gets caught on the field line and gets funneled onto the planet. For the interest of time, I didn't actually talk about that second effect, but that's something. It's a small twist on the accretion process. It's not super important for our story today, which is why I didn't emphasize it. But that's what that second line meant.
Okay, on the planetary mass function graph, what did the letter A represent?
On which graph?
The planetary mass function.
The letter?
PMF. I thought it was planetary mass function, but
yeah, there was a planetary mass function, but let me see.
Yeah, the A was in the numerator.
Let's see what we're talking.
Yeah, that one.
Oh, A is just the normalization constant.
Oh, okay.
If you integrate over all the masses, then the total amount of mass you have will be set by a normalization. So it's just a constant. It doesn't actually, it tells you how many planets you have, I guess. So again, it wasn't super important to the story, but.
Okay. And this graph that showed I guess where planets formed that had also tides in the upper left corner. I was wondering what the different iso lines represent. Yeah, that one. What did the different iso lines represent?
Oh, well, the story is that the iso lines correspond to how close you can get to the star. And the reason why they're on there is that if you have enough time, then tidal forces squeeze the planet and dissipate energy, and the stars or the planets will be hoovered into the stars.
Mm-hmm.
And if you're way in the upper left of this corner, you'll be hoovered in immediately. And if you wait forever, everything will be tidally hoovered in. So these different lines on this plot correspond to different time scales of billions of years. I don't remember exactly what numbers I put because I did this plot a while ago, but the different lines correspond to how much hoovering you get or how much tidal dissipation you get. And the range that I showed corresponds to how much you expect for the particular properties of stars in the particular ages, which are 3 to 10 billion years for the sample that we have, more like 3 to 6 billion years.
Okay, and my last question, the chart where you're showing the different planetary systems. I wasn't quite sure what the x-axis units were because it looks like if when looking at our solar system, it looks like you have at the unit 1 is that supposed to be your Uranus?
Oh, no, is it the plot that, can you see the plot on my screen?
Yeah, I can.
Yeah, 1 is 1 AU.
Oh, it is one. Oh, okay. I thought those were the outer planets. You
No, these are inner planets.
Okay.
See, all of them are like to the left of 1 AU except for a couple.
Got it.
If you look at the one called Sol, that's the one for the sun.
Mm-hmm.
The third planet from the sun has a value of exactly 1.
Got it. Yeah. Okay. Thank you.
Okay.
Wasn't there with that line.
All right.
Excellent, sir. Thank you.
I apologize to the in-person audience. We don't know why we lost the screens here.
Oh, well,
It seems to be your machine, but I don't know why. Because we can see it here, the Zoom audience can see it.
yeah, my machine's not talking to this machine this is a Mac and this is not, so
Right.
there's some communication gap.
Yes.
What we have here is a failure.
Actually,
Yes.
right now I'm just seeing Troy, I'm seeing you and Dr. Adams. I don't see anything else on the screen.
Really?
Okay.
Okay, presentation's over, fortunately. Anyway.
No, you're now free.
I think we should send you a gift certificate.
Oh, you don't need to send me. What you should do is you should take that funds and do something good for yourself. So
That's what our last speaker said too.
well,
INIPs.
Yeah. We'll think of something. Okay.
but it's all good. So
All right.
I'll see you guys soon.
Hope so.
Yep, till next time.
Okay. We can keep on accumulating stuff for Dr. Adams until it starts forming a planetesimal.
There you go.
All right. Yeah. Well, thanks so much for having me.
Thank you.
Always great to see you guys. Okay. You guys.
Hey.
Oh no, we got this. We got to roll.
I'm gonna move us along here because we got a couple things that might take a minute to call. The only thing I've got is Chelsea, the PTO event on January 30th. We now have 1, 2, 3, 4, 5, 7 of us going there. So not bad. I think we'll be well covered. And Glencairn, which was scheduled for, well, whenever it was, they canceled anyway and rescheduled for March 9th. And I think we've got maybe 3 people committed to that so far. So we'll work on that as we get a little bit closer. That's all I've got. So I will move to Tim.
Oh, okay. So I sent the board a sort of a rather lengthy word salad about where my thoughts were with the website. So I guess what I'm just gonna give a quick report. Barry had a big computer crash. His personal computer that he uses died in a quite severe way. So he's been trying to get himself back on board. It didn't affect the servers any. So I've been pulling the content from the old site. I've got Young Astronomers is in draft form now. It's done for Jack to look at. I've created some of the other pages. Pretty much my goal right now is to work on the site for what the public would see if they go to the club. Barry is working on the member part that we talked about, how we're gonna, try to do a more focused area where each member has a section that kind of member profile, and then within that you're going to hopefully have the ability to have your own gallery, your own pictures, blog, posting things, etc., etc. So that's going to come later. So the my priority is to bring the content over that would be consumable by the general public. Now, with that, I had a question for the board, and I'm just gonna throw it out. I don't know how you guys wanna go with this, but pretty much what I'd like to do, I had sent out a few emails asking for some input on a few things, observing sites. You know, Jim provided me a really great synopsis of that. I included that. That stuff is fine. What I would like to try to eliminate is me having to ask permission to put this in or that in. So I'm kind of thinking, what I want to give you right now is my kind of philosophy. So I'm looking at this from the standpoint of someone who I wonder what the lowbrows are about, or they find us through some other avenue. What would the public want to know about us? What would we want to be able to tell the public? So for my, I guess, 10,000-foot view of knowing you're the club since, when did I join? June, something like that. Is that one of the big things you do is outreach to schools like you've been doing, the open houses, participating in the star parties and other places around, the speakers that we have here. And there might be some other small areas, but those are the things I'm going to focus on first. There was a section in the website about how to observe, where to observe. Good stuff, all good materials. The how to observe was not completed from the old website, so part of it was there. And the other ones, the other 2 pages were just non-existent. They just they were just blank in the old site. So I'm going to begin to try to rebuild those. What's going to wait is all of the older articles and stuff that is years back. Right now it's too much to try to pull in. Barry is kind of looking at some ways when we're done to try to find a way, maybe we can have AI index it in some way so we can create an index with an archive instead of it just being a linkable thing. So that's going to be like the third priority. So in other words, I'm asking permission to just go ahead and take my vision of just what the club would be for other, for someone coming in and looking at it, what we generally do, having that there, and then letting me kind of do that. The last piece of this whole thing is I want to implement either Barry's going to do it online, we'll have a form, or I'll just have a Google form for links that'll be the club can have if there's like additions, edits, suggestions, that we can fill that out. So if I, for example, I leave something out that's important, or I put something in and it's like, nah, that really isn't that important, or whatever. That way I can go back and do some editing. Yeah, I hate email threads. I hate them with passion because we're talking about someone and someone responds with something completely different inside the thread, and then the thread ends up taking a left turn, and then I have
after a while we're lost.
Right, we don't know what we're doing. So anyhow, I think that's nice. So that's kind of my question. It's just to have some permission to be able to just go ahead and do it. And ask forgiveness later, I guess.
I suppose some discussion might be, my opinion is whatever you pull over is good.
Right.
Yeah.
Okay.
I would like the historic stuff mentioned.
Okay.
I find that very important to me personally.
Okay.
But, because there's a lot of people in there that with memories, I'd like to be able to keep them.
Right.
But whatever you're gonna pull first is fine.
Okay.
And focusing, from my point of view, and focusing on what the public's going to see is best.
Okay.
So we're not going to abandon.
No, that wasn't the case. It was just
It's priorities.
Yeah, it was a case of magnitude of how much stuff is there and the each.
Yeah. From my point of view, then what you're pulling in sounds fine. I don't know if we need
I personally,
any other discussion.
I like Dale's plan. I think we should give them great freedom to execute it.
Yeah, since I wrote a fair amount, that you have blanket permission.
There you go.
But there are some stuff I copied over.
Yeah, I don't know. I think what might be appropriate, and I don't know whether how you all feel about this, because like Ken just spoke about, I don't know the history because I'm new, and so I don't know what things are there that, and I'll be very honest with you, I don't have time to go back and read back to 1990, I think it's 1992 that was actually listed.
Yeah.
I don't have time to go back and read all that. It would be really good that if some people can begin the process, maybe of looking through it, what materials are still relevant in there. I don't know. I mean, are some of the articles timeless about, what they're talking about, or is some of the science has evolved? I don't know. So those are some things maybe people can begin to help with. I do know that I am going to be sending out some emails to the club at large saying, hey, and I did this with the observing sites, just for an example. Can someone give me some, ideas of where you observe? And Jim gave me a really good list that I included. Adrian, I did, and a few other people did. I know Norbert gave me a great list of places to visit. And I've now included that in the young astronomers that wasn't there before, because these places have now come about since that was published. So I will probably sending things like that, just to be getting input from people. Okay. Right. And I think we're going to be well within our time frame. Like I said, we might not have the member portal ready by then, but the public part of it, which is the most important for us right now, is going to be available.
I think we got the right guy for this job.
Yeah, my suggestion would be just get her up and running and sort it out later.
Hey, Jack.
Basically, I went out to the observatory another week and just checked the heating system and everything. Everything seems to be working all right. So we should be okay there. The only other thing I was going to talk about, and I think the other officers are going to talk about it anyway, is the open house schedule. What the dates, times, and how we're going to handle that this year. So that's really all I have to say.
We're going to get to that shortly.
Nice and clear.
Yeah.
Yeah, okay. Yeah.
I've been working on a brochure that we can hand out. And the officers are pretty much already in contact. And now we're going to the phase where I would like to get it printed. So I put a proposal out to the officers that we should print 200 copies. That would give us, every officer could have 10. We have other bucks to give to members to distribute. We get a price break at 200. So for 100, it's about $1.50 a piece. 200 is about a little over $1 a piece. So, but I can't do it until we have the open house schedule finalized. And I asked the officers to tell me who the proposal has. So I'll try to tell you. The cost would be about, I'd like to ask for $230 to cover. Like the rest of that.
Sounds good.
Okay, we have to vote.
No, it's 250, I think.
We don't have to vote. We have to vote. The officers have.
Right, I understand. The question was,
The officers to vote,
yeah.
they don't.
no, the question was, well, the question was whether we need a vote here or not.
We're not.
Okay.
So I will continue to press forward and get those.
And maybe this is a good point to look at that open house schedule.
Yes, we should.
Yeah. So this is what we've got, is once again laid out by Jim. We very much appreciate it. Takes some work to actually come up with this. Everybody that did comment on it seemed to be good with it. The question is in September, because around that time we get really clogged up with stuff. We've got astronomy at the beach, open houses. I believe September 5th, I think it might be the weekend before that, is I'm sure we're going to get asked to go back to Owasso. Unless that happens to be on September 5th, then we got to introduce not. Well, not necessarily, but Jim.
The Owasso, when I heard them talking,
Yeah, did you over, because I couldn't remember exactly what they said.
they try to run it the weekend before the Labor.
Okay,
Which this year I think would be like very end of August. If you look at that schedule, we've got 2 open houses. The first half. The next weekend is the club meeting picnic at Brian's. And then the last weekend is Owasso. It's a pretty busy August.
yep. And then right after that would be the September 5th open house coming up.
Yeah, now, my question about the entire schedule is we struggle to get Lowbrows to staff these events. I don't see any point in putting things in brochure that we're gonna have to live up to if we can't. And I was hoping there'd be a few more members. I don't know how many are still online, but that could say I can show up to at least one of these. Because that would go a long way to solidifying the schedule and as to what we should actually be doing as opposed to what we might dream about. And that leads to another discussion about how serious current club is about doing public outreach. But the core for the club, most of the years I've belonged to, has been these open houses.
Well, and a couple of years ago, we did threaten to cancel an open house if we didn't think we had enough people to actually help. And I believe one time we did do that. But I think the weather was a little shaky too, so we kind of had a little cover, but I hate to do that, but that's always an option. And if we had to do that, a couple times this season, then maybe that's telling us we need to reduce the schedule. But then again, the weather wipes out.
Weather wipes out a lot.
So.
And, there's, people have jobs, they have families, they go on vacation. And that's why some effort into recruiting people as far as they forward as they can see to commit to at least one of these dates. And then maybe go on from there to decide whether we're actually going to, which ones we will actually commit to.
How do we go about determining how many people?
Yeah, we'd have to get an answer or return on that pretty quickly. I don't know if we'd be able to.
I don't know how to, yeah.
And I'm gonna make as many of those as I can, but I'm just one.
And there are, you and Jack and a few others in the club.
And I already know
about showing up. Others, we hardly ever see.
I know. The majority of our members. But we have members spread out across the country. And I don't know where they're all.
Yeah.
The 200 and some that we've got, 213 or 200.
I'd be willing to bet that 3/4 of them live within an hour drive of each one.
Tim?
I belong to another group where we do something similar. I belong to the Ipsy Bike Club. We do booths at the farmers market. We run into the same thing in those same months. We've been going since May and we're burned out.
Yeah.
And one of the suggestions I have is just, even though we know the weather is an issue, maybe in August, September, pull it down to what? Just just because that tends to be,
Right.
that tends to be an issue. And that was, you know, only being in the group for a year, I just remember last year, that was. I remember
So that's also the best
September.
time of the year usually weather-wise, but then that's why there's so many events around that time, so.
Yeah,
Yeah,
But that's also when we first started them. We only did one a month.
yeah, it's way back, yeah. Yeah,
That's way back.
Yeah, well, the other thing we could do is. We could look at the months. And if we'd like to do a May 9th event, then we would do the 16th.
Well, that was my idea, the 16th would be a rain date, didn't do it on the 9th.
that's an idea to think about.
we publicize them, as we can publicize it like that.
Publicize the
Yeah,
first
yeah.
date, and then the rain date is the second date.
That's a
And so,
good
and
idea.
the first date, we don't do the second.
Yeah,
If it's cloudy the first date, then
It's
rain.
not a, that's.
yeah, I like that.
Yeah.
Much more wiggle room.
Yeah,
That is similar to what we did with
yeah,
Michigan Math and Science Group. We always had a rain date and observing group.
yeah,
Say,
let's do that.
That's a great
Anybody
idea.
opposed to it?
Yep.
You're opposed?
We still haven't,
Yeah.
We're so.
Very good.
Give it to a woman.
we still haven't figured out, we're gonna do both of them in September,
No.
as the Labor Day.
Yes, the question is still in September. Personally, I think maybe we should scratch the 5th. But then do we leave the 12th?
well,
we
the other question,
we have the 12th, you can do that, and the rain date is start in the beach. Beat out there,
Yeah,
because a lot of us go to that anyways.
true.
well,
It's not beach, but
this is the prize box.
yeah.
Okay, do you want to do that? So we leave the 12th and scratch the 5th?
So when I do that, I've already been doing the calendar on the website, that means, so we're gonna be consistent, the first date is our open house, and the second one is the rain date,
Yeah,
all the way down.
yeah,
Except for September.
yes,
So we'll just have the 12th listed.
Okay. and then-
Yeah.
Okay, I got it.
But
Yeah.
I'm sure you might want to put, it's trying to be at the beach. That date in there, some people.
oh yeah, we should have that, yeah, yeah,
Garden at the beach.
We should,
What are the dates for Stony Beach?
September 18th and 19th,
yeah,
which would be our third week. So in September, we're not gonna have our club meeting. Instead, we should tell everybody to go to Strawberry Beach.
Oh, so.
Yeah, because that's 18th, that's the third.
Yeah, it's been, for years now, there's a condo.
Right.
So we're not gonna have a club meeting
in September.
18th.
Right.
Instead, we'll be at Astronomy at the Beach.
Yeah.
So the week before, be an open house on the 12th.
It actually all fits in there rather nicely. When you think about it.
Well, the other thing I was gonna bring up was Uwasa was gonna be on the 28th and 29th. That would be the week before September 5th.
Right.
So we want some people to the Wasso event. Guess we didn't do the 5th. That would give them a little more leeway of doing another event. Because when you put them all together, you've got 4 weekend events all at one, right? That's not gonna work out.
Yeah.
That's just my thinking behind it.
All right, so I think what we're hearing there, see if we all agree, is the schedule is good. Except for September 5th, which we'll scratch. And otherwise, the first date will be the actual date. The second one of the month will be the rain date, with of course the exception of September.
Is the July meeting still gonna be at Scherzer?
Yes, yeah. July still be at Scherzer, and August, we are doing the picnic, but it'll be at Bryan Auto.
I'm not gonna put that on the website, that's.
Oh, that's true. Good idea, yeah, yeah.
Nor might not.
Well, on the other hand, if the public was bringing good food.
Double check.
Did I get to see your hand up? Somebody.
Well,
Oh, Don.
I don't, nor, I saw a communication Norman and I exchanged some emails, and he is filing paperwork to take a retirement on.
Yes, yes.
So it raises the question whether he will be available to give us access to Schuster.
Very good question.
I'll just leave the date on it then, I just won't put it on, I'll leave the location off.
Yeah, okay, just to be safe.
No, say to be determined.
Yep.
Yeah,
Not blank, but
Yeah.
yeah, TBD, yeah. Good one, Don, thanks for bringing that up. Wait a minute, we can't let Norm retire.
Solves the problem.
Well, from when I talked to him the other day, he's been discussing with other higher ups. They've all suggested he should retire.
Really?
Yeah, he's getting pressure.
Yeah.
He's 70.
Oh, yeah, he's 71, he's getting pressure, so that's why.
Yeah.
Easton has got financial
Got
problems.
it up there.
Got it. Okey dokey, we have an open house schedule.
Alright, we're good.
Okay,
The last part of my report is the last part of my report is I've sent a letter to Professor Renault asking him to present with it.
okay, thank you.
You can try.
we're just putting it on the website. Yeah, there's a place on the website to go over.
Yes, you haven't done that.
I haven't. So,
Yeah.
Christina sent in the events to the Observer for the month. So that's
She did see the one for next month.
I presume so.
Because I sent it to the officers. Did we add her to that, or you're just related?
Did not. So
Okay, take a, because we did get a title for that.
okay, I'll forward that to her. We'll have to get that.
Okay, all right.
I will talk to them. But other than that, no, I'm not.
Okay, Jeff.
To reiterate what's your name, Tim? What you say is like, Barry and Tim have been doing a great job and really pressing forward to it. I've started getting emails from the HostGator people who are hosting our current WordPress site, and they're, as Barry and I suspected, they are going to bump storage rates and whatnot. They want to go for us to go to the next plan since we fused more than they anticipated. They used to say that they were unlimited storage, unlimited bandwidth. Apparently, there are some limits. So our move to the alternate server is well timed, and the fact that they're on schedule to do that stuff is great, in spite of the lack of participation.
You want that on there?
No, that password's fine. That's the same.
What is that?
You guys all know. That's
Whatever you got on that page.
Oh. That was some stuff that Austin left for us.
You want that on there or not?
No, I was excellent.
Right now, we're with HostGator, but that contract is done on March 15th. And this is a month and a half out, and they're starting to analyze our usage, and they basically start, they're pushing us toward getting on the next tier plan, which is gonna cost a lot more money. And so